Alright, welcome to physical chemistry. We're going to start with chapter 1.1. The first thing we need to know, physical chemistry is the chemistry of everything that's interesting. We're going to use mathematics and the laws of chemistry to model bulk matter. This chart down here shows an example of what exactly we're doing. When you're doing a model, you can have very high system complexity, like you have with biology, because you have to worry about midi-chlorian, mitochondria, and all that. On the other hand, if you have a very simplified model, you end up with pure mathematics. So if you're going to do both, you're going to have some system complexity and some mathematics. Right here in the middle, we have physical chemistry. So you have to both memorize stuff and you have to understand mathematics. Okay, continuing on chapter 1.1, what exactly is physical chemistry? In chapter 1, we're going to be dealing with the properties of matter. Now these properties, they can be either microscopic or macroscopic. Microscopic properties, these are properties at the extremely small scale, like the atomic scale, molecular scale. Another name for this type of physical chemistry is chemical physics. Examples of these types of properties would be the size of the molecule, the shape of the molecule, the velocity of the molecule, momentum of the molecule, intermolecular forces such as London or dispersion forces. Hopefully if you're taking physical chemistry, you've already had exposure to some of this in your previous chemistry classes. Alright, continuing on chapter 1.1 of physical chemistry. Remember, chapter 1 we're dealing with the properties of matter, and we said that those could be either microscopic or macroscopic. Now, macroscopic properties are properties of bulk matter. Examples of these properties are like temperature, pressure, and viscosity. Now, also, physical chemistry has four main components, or branches, categories, however you want to talk about it. One is thermodynamics, which we're going to be doing very soon. 2 is quantum mechanics, which is microscopic. 3 is statistical mechanics, which is a bridge between the macroscopic scale and the microscopic scale. And then 4 is kinetics. And that's where we calculate rate of processes, such as rate of reactions and so on. Starting chapter 1.2 of physical chemistry, we're now going to talk about thermodynamics, which literally means heat power. Thermo means heat, dynamics means power. This is what we're going to be studying for about the next 10 chapters. There are several types of there are a couple different thermodynamic processes. One is equilibrium dynamics. This is what we're going to be doing for the next 10 chapters. And then 2 is irreversible dynamics, which we're not going to be covering. Equilibrium has 3 different categories. One, you can have mechanical equilibrium. Mechanical equilibrium means that there is no net force on the system. Your system is not under any kind of acceleration. Second type of equilibrium is material equilibrium, which means 2 things. One, there's no net material transfer into or out of the system. And secondly, there's no net reaction going on inside of the system. The third type of equilibrium is thermal equilibrium, which means that all parts of the system are at the same temperature, and therefore there is no net heat transfer within the system. Thermodynamic equilibrium means all 3 types of these equilibria are true. Continuing on, chapter 1.2 of physical chemistry, we're now talking about systems. The system is any part of the universe that we're interested in. It can be the contents of a test tube, a fractionated column, or even a cell inside your body. This class applies to systems of any scale. Really, really tiny systems all the way to planetary-sized systems and in between. There are 3 types of systems. One is an open system. Open system allows a transfer of matter and energy between the system and the surroundings. As you can see here, we have our system. It can allow matter and energy in. Matter and energy can also get out. A closed system allows transfer of energy, but not matter. Here's our system. Notice energy can get in and energy can get out, but not matter. An isolated system allows no transfer of energy or matter. We have our system. Nothing gets in, nothing gets out. Continuing on, chapter 1.2 of physical chemistry, the system and our surroundings are equal to the universe. The system is the part of the universe we're interested in. Everything else, at least what's relevant, is the surroundings. And all that together is equal to the universe. Now there are different ways of classifying the walls between the system and the surroundings. One, it could be rigid or non-rigid. If it's rigid, that means it can't move. If it's non-rigid, that means it can move. Another way is permeable versus impermeable. If it's permeable, that means matter can get through, kind of like a cell membrane. If it's impermeable, that means matter can't get through, like a typical wall. Another way to look at it is adiabatic versus non-adiabatic. Adiabatic means that heat or energy can't get, or does get, let me rewrite. Adiabatic means that heat can't get through, energy can't get through. Non-adiabatic, also known as diathermic, means that heat can get through. Dia means through, like dilate. All right. Thermodynamic properties. There are different examples here. So composition, that's what our system is made of. That's not actually particularly relevant. We're going to be doing ideal gases. Pressure, which we denote capital P. Temperature, which we denote capital T. The internal energy of the system, which we denote capital U. And then entropy, which we denote capital S. Continuing on chapter 1.2 of physical chemistry, we're still talking about thermodynamic properties. Thermodynamic properties can be either extensive or intensive. Extensive means it depends on the quantity. Examples of extensive variables are volume, mass, or heat. The important thing about extensive systems is if you have a larger system, larger value. Usually if you double the size of the system, you double the size of the value. An intensive system is one that doesn't depend on quantity. Examples of intensive variables are density, temperature, and pressure. And the important thing about intensive variables, whether you have a really large system or a really huge, small system, large, small, in between, the intensive variables will be constant. Now also we can divide systems into either homogeneous or heterogeneous. Homogeneous means it's only one phase. All intensive variables are constant throughout the system. So the temperature over here equals the temperature over there, etc. Normally this term would refer to mixtures of substances though, but you can apply it to pure substance, like homogeneous water, ice, I guess. Heterogeneous means you have more than one phase. Like you have ice floating in water, you've got two phases of the water. So it's a heterogeneous system. Finishing up chapter 1.2 of physical chemistry, first we'll define state. The state of the system is determined when we specify the minimum number of intensive variables. Extra would be redundant. For a pure substance, this number is 2. Examples would be like composition and temperature, assuming no external field. Also, we're going to define state function. The state function is a physical property that has a specific value after we know what the state of the system is. The state function is another name for thermodynamic property or thermodynamic variable. Example is volume, although keep in mind volume is extensive. So that's not technically true because you have to know the size of your system. The temperature is the property that tells us the direction of the flow of energy. We're not really in a position right now to define what temperature is, but this will give us a working definition for now. It's interesting, you can't technically measure temperature directly. For example, if you look at a thermometer to see what the temperature is, you're really seeing the volume of a liquid as a function of temperature. But even so, temperature is a very important, possibly the most important intensive quantity of a system. Partly because of what I just told you. It'll tell you which direction energy flows, which is always from the hotter temperature to the colder temperature. Later on, after we define what temperature is, we'll be better able to explain why energy always goes from the hottest temperature to the coldest temperature. But for now, we'll just assume it's true. All right, finishing up chapter 1.5 of physical chemistry, we're now talking about gas laws. The equation of state for an ideal gas is PV equals nRT. Remember, capital P is pressure, capital V is volume, lowercase n is the number of molecules. We'll talk about R in a bit. And then capital T is temperature. And if you watch the MIT version of the lectures, they basically divide both sides by n, so they have pressure times molar volume equals RT. That gives you intensive variables on both sides. In this version, you have two extensive variables, V and the N. So this gives you a good understanding of how large the system is. It's the same formula though. Both are the ideal gas law. Now R is called the universal gas constant, and it can be written in different ways depending on what unit system you are using. For example, you have 0.08206 liter atmospheres per mole Kelvin, or you have 1.987 calories per mole Kelvin. The one that we're almost always going to use is 8.314 joules per mole Kelvin. And then the final one is 82.06 centimeters cubed per atmosphere. Notice in each of those cases, the numerator is in units of energy. In fact, in the ideal gas equation, both of these sides are equal to units of energy. That's one of the reasons that it's written like that, instead of, say, solving for P and writing it as a fraction. Now, the ideal gas law that we're going to assume is basically valid at low pressure. The reason is the ideal gas law, it assumes two things that are not really true of an actual gas. One, it assumes the molecules have no actual volume. This is because we're dealing with such low pressure, the molecules are so far apart, the gas is mostly empty space. So that's somewhat valid approximation. The other assumption the ideal gas law makes is that there are no intermolecular forces. And again, in a typical gas, like what I'm breathing right now, the molecules are so far apart, it's mostly empty space that you don't have strong intermolecular forces. Of course, if you did, then they would condense and form a liquid, but that's another chapter. Continuing chapter 1.7 of physical chemistry, now we have a real gas law, an example of which would be the van der Waals equation. Van der Waals equation can be written like this. P is equal to nRT over B minus NB minus AN squared over B squared. A and B are both constant terms, and they're specific to the gas that we're analyzing. Now, the A corrects for pressure, and is subtracted because it's based on intermolecular forces. Intermolecular forces are always attractions. Those intermolecular attractions, therefore, if the gas is attracted to itself, it's not pushing as hard on the wall. So this is going to reduce the amount of pressure on the wall of our system. Now, the B term is just a volume correction term, which compensates for the actual physical volume of the molecules. Now, rewriting it more like PV equals nRT, so this here is our pressure term with our A correction added in, and then this here is our B term with the volume subtracted out, but it's still equal to nRT. In this class, we're not going to be using this though. We're going to be assuming ideal gases. So if you put in A equals 0 and B equals 0 and simplify, you'll notice that it's still equal to PV equals nRT. Okay, continuing on in chapter 1.7 of physical chemistry, we're going to talk about PVT behavior as it in any phase, even condensed phases. Remember, liquid and solid are the condensed phases because of the intermolecular attractions holding molecules together. Gas is the only phase that's not condensed phase. So for any substance, volume is a function of temperature and pressure. That's assuming that n is constant. The number, remember, lowercase n is the number of molecules. And F is just some function that we're not going to define right now. Although for the ideal gas, we already defined it, P equals nRT. So D, capital V, the D means it's differential. So we have dV is the change in volume instantaneously, just like in differential calculus. Now this is the slope formula then to find volume as a function of temperature and pressure. One, we're going to find the derivative of volume with respect to temperature, holding pressure constant. And then the other is the derivative of volume with respect to pressure, holding temperature constant. This is an extensive form. of the equation, because if we were to integrate that, we would end up with the total volume of the system. So dV is a total differential. If you don't know what that means, take differential equations. And again, this is an extensive quantity. It's our volume, change in volume at any time. Now we can take this whole equation and divide by V. That's just algebra. So now we have the derivative of volume with respect to volume times 1 over volume times the derivative of volume with respect to temperature at constant pressure as that changes with temperature, plus 1 over volume times the derivative of volume with respect to pressure at constant temperature times the differential of pressure. This is the exact same equation, except now it's intensive. If you take an extensive quantity and divide by another extensive quantity, they'll kind of sort of cancel out, and now you've got an intensive quantity. Now these terms right here have very special names. This one here is alpha. So alpha is 1 over V times the derivative of volume with respect to temperature at constant pressure. Notice there's no dt term here. So this is the Greek letter alpha, and this is the coefficient of thermal expansion, also known as the cubic expansion coefficient. Be careful, because there is another coefficient of thermal expansion that would only be linear. That's why this one's called cubic, because it's the change in volume, not just in one dimension. Now this term here, as volume changes with pressure, is going to be negative. So we're actually defining minus kappa as 1 over V times the derivative of volume with respect to pressure at constant temperature. So I know my kappa looks suspiciously like the letter K, but we'll pretend. So kappa, this is isothermal compressibility, because isothermal means constant temperature. That's what this means. This P means we're holding at constant pressure. This T means we're holding at constant temperature. Now this term, like I said, is going to be negative, because as pressure increases, volume will decrease and vice versa. So putting the minus sign here means we're going to end up with a positive value for kappa. Continuing on chapter 1.7 of physical chemistry, we're going to define molar volume as V volume over N. So remember, capital V is volume, lowercase n is the number of molecules measured in moles, and then, like I said, capital V subscript lowercase m is molar volume. So we defined alpha already as 1 over volume times the derivative of volume with respect to temperature at constant pressure. We could also, if we were working in intensive quantities for some reason, we could write it as 1 over the molar volume times the derivative of molar volume with respect to temperature and pressure, with respect to constant pressure. Likewise, kappa, we define that as minus 1 over V times the derivative of volume with respect to pressure at constant temperature. But again, if we, for some reason, had intensive quantities, then we'd have minus 1 over molar volume times the derivative of molar volume with respect to pressure at constant temperature. So our definition, we already had intensive quantities, but if you divide an intensive quantity by another intensive quantity, you still have an intensive quantity. Now, example of values for alpha. For solids, they go from about 10 to the minus 5 per Kelvin to 10 to the minus 4 per Kelvin. For liquids, it goes to about 10 to the minus 3.5 per Kelvin to 10 to the minus 3 per Kelvin. And for gases, it's more like 10 to the minus 3 per Kelvin to 10 to the minus 2 per Kelvin. Likewise, values for kappa, typical value ranges 10 to the minus 6 per atmosphere to 10 to the minus 5 per atmosphere for solids. Liquids, it's more like 10 to the minus 4 per atmosphere and higher. And then for gases, it's more like 0.1 per atmosphere to 1 per atmosphere. Liquid is the most complicated phase, though, because you have your intermolecular attractions, but you also can have chemistry and so on reactions. Kappa is considered a function of temperature and pressure, while alpha is considered a function of temperature and volume. Okay, finishing up chapter 1.7 and chapter 1 in general of physical chemistry. Let's do an example, because we haven't done any actual calculations yet. Let's say we want to calculate the volume change that occurs when 50 centimeters cubed of argon, treated as an ideal gas, is heated through 5.0 kelvins at 298 kelvins. Now that seems like an oxymoron, but it's a simplification I'll show you in a little bit here. So basically, let's say we're going to heat it through 5 kelvins starting at 298 kelvins. Okay, so we're going to assume constant pressure. Now let's find delta V. Now remember, dV is a function of, I forgot the dP. Temperature and pressure. Therefore, we have the derivative of volume with respect to temperature at constant pressure times the differential of T is equal to the derivative of volume with respect to pressure at constant temperature times the derivative of pressure. Again, if you don't understand that, take differential equations, but just assume it's true for now if you haven't had differential equations. Okay, so remember, we're assuming P is constant. So this differential is equal to 0, which means this entire term is equal to 0. So that's what we've got here. The partial derivative of volume with respect to pressure holding temperature constant times the differential of P is equal to 0, since we assumed constant pressure. That's just one of the simplifications we're making to keep the mathematics reasonable. Now that's for a differential, which is an infinitesimal change in volume. What we're trying to find is delta V, which is a finite change in volume. So what we're basically going to do is assume a lot of things that are constant to simplify the math. So what we have is the change in volume is roughly equal to the change in volume with respect to temperature at constant pressure times delta T. And the reason we're doing that is we're assuming this is constant, etc. Now remember, we defined alpha as 1 over the volume times the derivative of volume with respect to temperature at constant pressure. Now if you multiply both sides by V, then you'd end up with alpha V is equal to the derivative of volume with respect to temperature at constant pressure. That's the substitution I made here. I replaced this term with this right here. So now what we have is the change in volume is approximately equal to alpha times volume times the change in temperature. Now we assumed that argon is an ideal gas, so what we want to do is go ahead and find what is alpha for an ideal gas. So we start with the definition of alpha again. This 1 over V times the derivative of V with respect to temperature at constant pressure. And what we're going to do is use the ideal gas law. V equals nRT, so substitute in nRT over P. The reason we're doing that is because, we're finding the derivative with respect to temperature, so we can't have V in there. We need to instead have temperature in there. So when we do this, nR, those are constants, so we're pulling that out of the derivative. And P, we assumed is constant pressure, so we're going to pull that out of the derivative. So we're going to find the derivative of just T with respect to T. Obviously, the derivative of a variable with respect to itself is just 1. So what we end up with is the 1 over V, and all those constants we pulled out, times 1. Then using PV equals nRT again, we're going to simplify this to get 1 over T. So what we have shown is for an ideal gas, alpha is 1 over temperature. Now we can finish up finding the volume change with argon. So again, we have the change in volume is roughly equal to the change in volume with respect to temperature constant P times delta T. Since this is alpha, we're substituting our alpha V, so alpha is 1 over T times V, and then times delta T. So we have 50 centimeters cubed, we were given that in the problem, times 5 kelvins, and then divide by 298 kelvins. This is the simplification we're making. If we were going to do the calculus for real, of course, this temperature is changing and the math would be a lot uglier. So what this tells us is the volume would change by less than 1 centimeter cubed, 0.84 centimeter cubed.